Hi, welcome to Mathematics with Tom. I am Tom, and today we are going to take a look at the logistic equation. And I've written it out here, and I've written it in its general form. The general form is that y prime is equal to ay minus by squared, where a and b are just both positive numbers. Now, there's also another aspect of this. Since, oops, wrong tool there. Since the equation is only a function of y, this is called an autonomous differential equation. Autonomous differential equation. And what I mean by that is we've been studying problems of this form: y prime equals ay plus some function of t, q of t. We've looked at a heavy side, an exponential, the delta function. Well, in this case, notice there's no q of t. Everything is either y prime or y. So that's what makes this a unique equation. And as a result of that, we can study what this equation looks like without even knowing the immediate solution to the equation. And that's what we're going to do now. And we're going to do that with an example. Here's our example. Our example is that y prime is equal to 3 times y minus y squared. I think that should be a pretty good example. And our goal, what we're going to do, is sketch the solution. Okay. There's one more thing I need to tell you about the autonomous differential equation. And that is since the right side of the equation is just a function of y's, we often refer to the right side as a function by itself. So we're going to spend much of our time here just examining the right-hand side. And so that we have an easy way to reference it, what we often say in general, so I'll write this both ways. Oops, that's not quite general. The general form is that we have y prime, if it equals ay minus by squared, we say that the right-hand side, we just call that the function f of y. So in our specific example, so for this example, specific example, we have y prime equals 3y minus y squared equals f of y. And so another way of just thinking of that is simply as the f of y is equal to 3y minus y squared. And it's with this f of y that we can actually understand y, the unknown function. So notice that f of y, it represents a derivative. Let's just start looking for roots. Let's look for roots. In other words, the roots are when f of y is equal to 0. All right, well, let's find out when that happens. So the 0 is equal to 3y minus y squared. I'm going to factor this, so I have a y times 3 minus y equals 0, and that would give me solutions then of y equals 0 and y equals 3. Okay, so what does that mean? That means that we have a 0 slope for the function of y, even though we don't know what the function is. We have 0 slope at y is 3 and y is 0. And it's with that information that we can begin constructing a picture. So we'll do this in many pieces here. So I'm going to make myself a graph here. Okay, so I have 0, let's go 1, 2, 3, maybe even go up to a 4. It was not a very straight looking line there, was it? Let's make that straight. There we go. 3, 4. Now I'm going to start adding some colors here. So I'm going to just put this dashed line right here at y equals 0. Oh, let's label this. So this is the vertical axis is y, and the horizontal axis is t. So the function of y has a 0 slope. At 0, and it also has a 0 slope here at 3. So let's put that in here as a dashed line. Okay, well, what does that tell us? It gets us started actually surprisingly quickly. I'm going to make a few sketches here, of which I hope you don't write, because none of these are correct, but I would like to use it to build some intuition. And then we're going to clear them all off. So let's say I started up here maybe at 4. Well, if I started up here at 4, my function might go up, in which case it's in no way affected by these derivatives with the areas where the derivative is 0. However, if I started coming down to this equation, well, I can't pass through that, because in order to pass through that, I would have to have a negative slope when I hit 3, but I wouldn't. I would have a horizontal slope. So in other words, maybe this rebounds. So notice that I started out being concave down, and then I changed to concave up. That would imply there'd be an inflection point there. So we might have to take a look at some of those. Or maybe the equation starts at 3, and then it just kind of gets close to 0, like an asymptote. Okay, then let's say we started here at 2. Well, we don't know if we're going to go down or up. Maybe I start going down. Well, if I start going down, I get to the 0 slope. So maybe I'd have a 0 spot there. Maybe it rebounds. But it would have to rebound again, because it can't pass through that, because it would have to have a non-zero slope to go above the 3, to pass through 3, or to pass below the 0. So maybe my solution is some kind of a sinusoidal. We'll see. And then maybe it starts down here at -1. Well, it might come up. Again, it can't pass through, but maybe it's just asymptotic, or maybe it just rockets into -infinity. So how can we build some more understanding? Let me clear our graph, and let's try this. Well, a few things. One is we want to know, well, is the function increasing or decreasing? That would be one thing to know. And also another thing would be to know its inflection points. So before we continue, I know I'm going to run out of space. I'm going to copy my picture. I'm going to move this onto another page. So hold on a moment, and I'll be right there. Okay. So I've put our graph over here, and let's recall also what we said. We have our f of y. I'll write it again. We have the f of y is 3y minus 3y minus y squared. And remember, that's the derivative of y prime. So that would tell us if we're in an interval, if something is going up or if something is going down. Let's continue one more step before we start calculating these things. Let's try this. So let's do this. Let's pick a value in each of these 3 areas. So we need a value in the area where y is above 3. We need a value for y between 0 and 3, and then a value for y when y is beneath 0. And what we're going to do with each of these is we're going to find out, is our function, the slope of our function, is it increasing or is it decreasing? So let's do this. And I'm going to do this in another color, because then we're going to mark these up. Oh, let's use it. That doesn't. We'll add that later. Okay, so an easy value to pick that's greater than 3, I'm thinking of 4. So let's try 4. So let's see, what is our function doing at 4? So, f of 4, this is going to be 3 times 4 minus 3 squared. Well, that's going to be 12 minus 9, that's going to be 3. And it's not just the 3 that we're after, it's the positive value. So, oh goodness, if I could do my arithmetic. 3 times 4 minus, minus 4 squared. Well, that's 12 minus 16. Oh, I was way off. This is minus 4. So in other words, our slope is decreasing. So let's put f of y up here is less than 0. So that way we know that it's decreasing. Let's continue to do that for the next interval here. So this, let's try, how about 2? Or, oh, 1. 1's a nice one. So how about f of 1? Well, that's going to be 3 times a 1 minus a 1 squared. That's going to be 3 minus 1. That's going to be 2. So in this middle section here, now I have the derivative f of y is greater than 0. So it's increasing. Well, that's kind of strange. How is it going to be increasing yet? It's bounded. It can't break through that zero slope. All right, the next one, let's try -1. So we're below 0 now. F of minus 1, this is going to be 3 times minus 1 minus 1 squared. Well, this is going to be a minus 3 minus another 1, so that's going to be a minus 4. So when we're at minus 1, here we have a slope of minus 4. So here, f of y is less than 0. Okay, we can do a little bit more now that'll help. And that little bit more comes from if we knew the second derivative of y. Well, that would just be f prime of y. Because what would f prime, the second derivative tells us how the curve bends, and it tells us when it changes the bend. So if it's a positive slope, if it's positive, then we have a curve that's concave up. If we have our second derivative is negative, we have it concave down. And then, of course, the interesting question is, what about 0? And when it's 0, we have an inflection point. An inflection point is where something goes from being concave down to where it becomes concave up. That moment at which the function changes direction is our inflection point. So let's find the second derivative, or f prime of y. Well, let's see. Remember that f of y, that's 3y. Well, the derivative of 3y, that's going to be 3 times dy dt. Well, that's just y prime. Oh, yeah, we have to remember that. Minus 2 times y times the derivative of y. Well, that's y prime. Let's factor that out. So now I have a 3 minus 2y times y prime. Okay, I think we got that then. And I'm not that should be enough information. We could write it as this way, 3y, or 3 minus 2y times y prime, which is 3y minus y squared. But if we have to use values we've already calculated, like if we use a 4, a 1, or a -1, we already know those values for y prime. Now, what else can we do with this? Oh, well, let's see if there's any inflection points in this. So inflection points come when f prime of y, which is 3 minus 2y times 3y minus y squared is equal to 0. This will give us our inflection points. Well, what we have to solve is we have to solve both factors at 0. So 3 minus 2y equals 0. Well, that's going to give us, that would give us y equals 3 over 2. And the other part of this is that we've already solved when 3y minus y squared equals 0. We've already done, so we know that y equals 0 and 3 again. So that's the horizontal point. So you can have anomalies in inflection points as well, and which is what it looks like we're going to have here. So the main inflection point of interest then is going to be this 3/2. So I'm going to put that 3/2 in. Let's put it in this nice kind of pinkish color. So 3/2 is right here. And that's my inflection point, meaning this is where the curve changes. All right, now let's try this again. Let's see if the curve is concave up or concave down. And again, we'll start in each of these different regions, plus we're going to have to split the region between 3 and 0. So let's try again. So now f prime of 4, well, this is going to equal, ready? 3 minus 2 times 4 times f of 4. Remember, that's just right here. Y prime is the same as f of y. Well, we've already figured this out, so this is going to be 3 minus 8. So that's going to be a -5. And then the f of 4 we already figured out. We already figured that out right there. Oh, yes. Okay, I had to think about that for a moment. So -5 times, we have a -4. So this is a +20. In other words, in the region above 3, it's concave up. Concave up. Okay, and then let's continue. So now let's actually look at something where when y is less than 3, but it's above the inflection point of 3/2. So how about 2? So let's try f prime of 2. So that's going to be a 3 minus 2 times 2. And then we're going to have to calculate that one. So this is going to be a 3 times 2 minus 2 squared. Well, that's going to be a 3 minus 4. That's -1. And then I have a 6 minus 4 for 2. So this is a -2. This is concave down. And let's try 1. So f prime of 1, oh, that shouldn't be so bad. That's going to be a 3 minus 2 times 1 times, and we've already figured out what f of 1 was. Well, so this is going to be a 3 minus 2. That's going to be a 1. F of 1 was a 2, so this is 2, so this is concave up. And finally, how about when we're below y? So now we would have, let's try f prime of -1. That's going to be 3 minus 2 times -1 times f of -1. Well, that's going to be a 3 plus 2, that's 5. And f of -1 is -4. This is -20. That's concave down. Now, look at this. We can put all of this together. Here's how we can do that. First, let's grab a different color to do this. And let's start. So let's look at our first pieces. When we started at 4, if we started at 4, we know that from this piece, we know that the slope is negative, so it's going down. And also, we know that it's concave up from f prime of 4. So I have something that maybe if it starts here at 4, it has some kind of a curve. It's up, faces up, but there's no inflection point. So it's going to just keep going out like this. Now you might say, well, how do you know it doesn't bend back up and be concave up? Because then otherwise the derivative would change, and it would have gone from a negative derivative back to a positive derivative. So it just keeps going down. That's all it can do. Let's go for the next easier one. The next easier one that we could look at is when f when we start at -1. So we're going to start at -1. And notice that we said here the derivative is 0 and it's concave down. So that means it's always decreasing and it's cupped in the downward way. So this solution just goes like this. And actually when you graph this, it goes down very quickly. And then the interesting part is in between here. It doesn't matter where I start. Say I pick we started at 1. We've calculated that. So if I started at 1, well, what do we know about that? Well, what we said in here is the function is always going up. But when we started at 1, it's concave up. But when we get above the inflection point, it's concave down. So it's going to come up. It's going to be, it would pass through 1. It's concave up. It's going to hit the inflection point. So that means now at the inflection point, the concavity changes. It's going to be concave down, but it's going to continue rising up towards that 0. Because remember, the derivative always stays 0. It should be getting closer. Mine kind of seemed like it was going away, but it's not supposed to. This is called the S-curve. And that is the general picture of the logistic equation. In the next videos, we're going to be looking at 1, how to solve it, and 2, what phenomenon it actually explains. I hope that helps, and thanks for watching.